Okay, so in this chapter we'll continue our study of motion, and we'll look at motion in 2 and 3 dimensions. We'll define the position and displacement of a particle, the average and instantaneous velocity, average and instantaneous acceleration, and then we'll look at projectile motion. Here's the projectile motion, and this happens in 2 dimensions. We'll look at uniform circular motion, an object going in a circle at constant speed, and then relative motion. Okay. All right, so here's a three-dimensional coordinate system, x, y, z, and here is a particle, and its position vector with reference to this coordinate system is given by a vector from the origin to its location. And of course, here's its x, y, and z coordinates. So here's the x coordinate, here's the y coordinate, here's the z coordinate. So x, y coordinate, and z coordinate. And now as this particle is moving, the x, y, and z coordinates will be functions of time. And this here is a complete description of the motion if you have these 3 functions of time. So that would be a description of a motion in 3 dimensions. So if this is the brown line is the trajectory of the particle, the displacement vector is, so if the particle is here at instant 1 and there at instant 2, the displacement vector is defined as delta r, which is a vector pointing from the first location to the second location, and that's equal to r2 minus r1. So there is the displacement vector. Now we define the average velocity between these 2 instants. The average velocity is defined as the displacement vector divided by the time over which that displacement happened. And velocity is a vector, and the displacement is a vector. A vector divided by a scalar is a vector. So anyway, the velocity vector will point in the same direction as the displacement vector, except its length will be different. Okay, what we are interested in mostly is instantaneous velocity. Instantaneous velocity is the average velocity in the limit delta t going to 0. And that, as you learned in your calculus classes, is the time derivative of the position vector. Okay, so the x, and all right, let me write this. V is dr by dt, which is d by dt of xt I plus yt j plus zt k. And so this would be dx by dt I plus dy by dt j plus dz by dt k. And this would be the x component of the velocity, this would be the y component of the velocity, and this would be the z component of the velocity, right there. It turns out that the magnitude of the instantaneous velocity is the instantaneous speed. You might want to go to this Wikipedia site and look at curved trajectories and stuff like that, and it'll tell you about the curvature of a trajectory. Now, we are also interested in a quantity called acceleration, and acceleration is denoted by a. You have acceleration when your velocity is changing with time. An average acceleration is defined as the change in velocity divided by the time over which this change happened. So there's the change in velocity and there's the time over which happened. So here's a diagram that shows you. So the blue line is the trajectory of a particle, so maybe a plane is flying along like that. When the plane is there, that's its velocity. The velocity is tangent to its trajectory. And when it's there, the velocity is tangent to its trajectory there. So there's the velocity. Now you can see obviously the velocities change. Now the velocity can change by changing its magnitude, that's the speed, or changing direction. In this case, direction is changed, and the also it seems like it slowed down a little, and the magnitude has changed as well. Anyway, you will have acceleration as long as the velocity changes. It doesn't matter how the velocity changes. It could be just the magnitude changing, it could be just the direction changing, or it could be both changing. So as long as you have a change in velocity, you will have acceleration. So for instance, in this projectile motion, you can see that the y component of the velocity is changing. Okay, the x component doesn't change, and that would mean that there's no acceleration in that direction, in the x direction, and we'll talk about this more. Anyway, so you have acceleration as long as your velocity is changing, and average acceleration is change in velocity divided by change in time. Again, as in the previous case, we are interested in instantaneous acceleration. Instantaneous acceleration is average acceleration in the limit delta t going to 0. So that's dv by dt. So ax is dvx by dt, ay is dvy by dt, az is dvz by dt. Okay. So again, you have acceleration when your velocity changes. So let me do an example. RT is so I'm just going to make up 70 I plus 70Q plus 3TJ plus 40. Okay. So here's I've described a motion to you guys. Here's a position as a function of time. Oops. And we will calculate the velocity of this object as a function of time. This dr by dt. And if you take the derivatives, this is 10t plus 7. Oops. 10t plus 7 I. That's 27 times 3 is 21t squared plus 3j plus 4k. And the acceleration would be dv by dt, and that would be 10I plus 42tj plus 0k. So there you go. Given the position as a function of time, you can calculate its velocity, the velocity of the object, and the acceleration of the object.